So far, we've been talking a lot about gravitational forces, but gravity is different from other contact forces that we've seen. When I push a wooden desk across the floor, the desk moves because my hands are in contact with the wood. But with gravity, objects pull on each other even when they're not in contact. Mass has this way of reaching across empty space and pulling on other mass. And in physics, we describe this feature where mass reaches out across space. We describe that using something we call a gravitational field. So remember in our picture we said that M1 and M2 pull on each other without being in contact. We call those pulls, those forces, we call it a field force because it operates through a quote-unquote gravitational field. So here's a quick and dirty way of understanding what a gravitational field is. A cornfield is just a region of space where you find corn. A gravitational field is just a region of space where you find gravity. So where do we find gravity? Well, we find gravity around mass. Every single mass is surrounded by its own gravitational field. And the field extends out forever, all the way into infinity, across the entire universe. So imagine this circle here is just a little chunk of mass, a spherical mass. We draw the gravitational field around it using something called field lines. And here are what field lines look like. Now don't worry about the arrows yet. It might seem like they're pointing in the wrong direction, but we'll talk about those in just a bit. So imagine we take another little mass, which I'll call little m, and we place it in big M's field. Little m, because it has mass, will get pulled on by big M. It'll feel a gravitational force pulling it toward big M. Now this picture actually shows us the very definition of a gravitational field, the formal definition that we must know. A gravitational field is defined as a region of space surrounding a mass where a gravitational force would be produced on another mass. So it's defined as a region of space, which is where the lines are, the field lines, surrounding a mass, big M, where a gravitational force, F, would be produced on another mass, little m. So in our picture, the object, the mass that produces the gravitational field, is called the source mass, big M. So big M is the source mass. And it's the source because that's whose field we are thinking about. That's the field that we're looking at. We're looking at big M's field, and we're not looking at little m's field. In fact, we ignore any gravitational field that little m has, which means we call little m, the second mass, which is placed in the field, we call it a test mass. And here's why it's a test mass. So there's our test mass. Little m is only used for purposes of finding out whether there would be a gravitational force F produced at this location. The only reason we need little m is to find out whether or not it would feel a force. And if it does feel a force, then we know that it's in the presence of a field. Right? So we only care about the field produced by big M, and we're not looking at whether or not little m has a field, so we just call it a test mass. We're ignoring its field. The field lines have arrows that point in the direction where the test mass would travel if it were released. So here's my source mass. If I put a test mass right here, it would travel this way. If I put a test mass here, it would travel that way. If I put it here, it would feel a force pulling it in toward big M. So it'd get pulled in toward big M and it would travel this way. At the top, it would travel down, and so forth. So all of those lines are the field lines, right? If we were to release the little m, the source mass, the test mass, at any location on one of these lines, then the line shows where little m would travel once released. And we notice that the gravitational field lines point in the same direction as the gravitational force. Because if you put a little mass right here, then it's going to feel a force pointing up toward big M. And the field line also points up. So those two things, the gravitational force and the field lines, point in the same direction. Now, these field lines, even though we show them starting somewhere on the page, like right here is where this one starts, they actually start all the way out here beyond the edge of the paper at infinity. And they travel all the way down along the paper, and they terminate at the source mass, m. At locations on the page where the field lines are really close together, the G field is stronger. The gravitational field is stronger. At locations where the field lines are farther apart and more spread out, the G field is weaker. So right here, okay, all the field lines in the surrounding area and the nearby area are really close together, which means we have a strong field close to the source mass. And as we travel out away from the source mass, now the field lines are spread out, right? Which means the field is weaker. So the way we say this succinctly is we say that the density of field lines indicates the strength of the gravitational field. Now, if we look at this picture, we notice that all of those field lines extend out along radii starting at the center of my source mass. So you imagine here, right here where my mouse is the center of the source mass, and then these field lines extend out along radii. And the way we describe this in physics is we say that the field lines around a point mass and a source mass, we say that they're radial. Now, gravitational field strength, it's not just something that we can look at qualitatively by examining field lines, right? It's actually a number, it's a quantity. And it's not just any quantity, it's a vector quantity. And because it's a vector quantity, we will use it and we will draw it in our pictures as an arrow, right? Just like we draw every vector. And because it's a vector quantity, it has magnitude and direction. And the magnitude is calculated through an equation. We use equations to calculate magnitudes, to calculate numbers, amounts. And gravitational field strength is a property of points in space. So in fact, every single point in space has its own gravitational field strength. Those points might, two different points in space might have the same number as the field strength, or they might have different numbers as the strength, depending on how strong the field is at those 2 points. So imagine we have some source mass, m, and we want to know what the gravitational field strength is at this random point, P, and P is separated from the center of the source mass by a distance that I'll call R1. Here's the equation we can use for calculating the gravitational field strength, which is given the variable g, at some distance from the center of the mass, m. So the gravitational field strength is calculated using the same universal constant, big G, times the mass of the source, big M, divided by r squared, where r is the distance from the center of my source mass to the point that I'm looking at. So in this example, right, the gravitational field strength at P in my picture, this point P here, is equal to big G times m, the mass, divided by r1 squared, since r1 is the distance from the center of the source mass to the point. So what we see is that when we're dealing with a source mass like this, G, which is the magnitude of the gravitational field strength, G depends on two things. Right? Big G is fixed, it never changes. So little g depends on m, the size of the source mass, or the mass, m. Really what I mean here is the mass, is it 5 kilograms or 10? And g also depends on r, right? Which in this case was r1. Depends on how far the point is from the center of the source mass. Now the units for measuring the gravitational field strength are newtons per meter, and we'll see why in a little bit. So let's take a look at our equation for G field strength. We see that G field, right, the gravitational field strength, is directly proportional to the source mass. That means that if we increase the source mass, we'll increase the G field strength. Now, of course, we assume that we're not changing the distance r. And likewise, if we decrease the source mass, big M, then we'll decrease G, the field strength. And so here's an example. Let's say we have a 4 kilogram source mass, and at a fixed distance of 1 meter away, we have this point P. So the value of G at this point P is going to be big G times 4. We plug in the mass, it's 4. And then the denominator, we have r squared, so that's 1 squared. And ignoring units just for a second here, the value of G, the field strength, at this point P is 4 times the universal constant. But what if I had an 8 kilogram mass like this? So instead of a 4 mass, now I'm changing it to an 8 kilogram mass. Well, the new gravitational field strength, G prime, at this point P, now the gravitational field strength at P has changed, and instead, in the numerator, we plug in 8, the bigger mass, the new mass. And 1, of course, is still the distance, so the denominator is still 1 squared. And what we get as the new gravitational field strength is 8 times the universal gravitational constant, 8g. And so you see that if we double the source mass, it went from 4 to 8, then the field strength will change by going from 4g to 8g. So the field strength will also double if we double the mass. And looking at this equation, we see G, the field strength, is proportional to the inverse of r squared. Right? That means that if we change the separation distance by some factor, like if we increase the separation distance by a factor, then we'll decrease the G field strength by the factor squared. And of course, that assumes that the mass doesn't change. It must stay the same. So let's look at that scenario. Here's my 4 kilogram source mass, and I've got this first point, P, which is 1 meter away. The value of the field strength at P is big G times the mass, 4, divided by the distance, 1 squared, and that gives us 4G. Now I'm going to double the distance, r. So I look at point Q, which is 2 meters away instead of 1 meter away. And let's find this field strength at Q. Well, it's big G times the same mass, m, which is 4, right? M is in the numerator, so we plug in 4. And in the denominator, we have now 2 squared, which becomes 4. And it's G times 4 over 4, which is simply equal to G. So if we double the separation distance, if we multiply it by 2, then we divide the gravitational field strength by 4, because it went from 4g down to just g. So imagine I have this source mass, and the mass of it is big M, and then I have this random point P, and P is separated from the center of the source by a distance r1. Well, we've seen already that the value of the gravitational field strength at this point P, right, G at P, is big G times the mass divided by r1 squared. But what if I had point P down here? Well, it's still separated by r1, so this is still r1 squared. The mass hasn't changed, so this is still big M, and G never changes, so what we see is that it's the same value as the field strength up here. So by swinging this point P down to here, we haven't changed the field strength's magnitude, because nothing in the equation has changed. So I could move point P to anywhere on a circle whose radius is r1, and the field strength will be equal to this, the right side of this equation. So the interesting thing we see is that the G field strength, due to a source mass, m, does not change as you move around a circle centered on the source mass. Only as you move out or in radially do you change the field strength.